All right, let's dive right in, shall we? We've got a ton of research and articles here all about data quality, especially for data science.
Sounds like someone's ready to go deep. And you're right, this is way more than just like fixing typos.
Yeah, I'm ready to move past the basics. We're talking data dimensions, governance, frameworks, the whole data quality shebang.
I like the way you think. It's like we're prepping for an expedition into a data jungle.
Oh, I like that analogy. But why is data quality such a big deal? Don't we have powerful AI and algorithms now? Can't they handle a little messiness in the data?
That's a really common thought, but even the most advanced AI is only as good as the data it's fed.
So it's kind of like you can't build a skyscraper on a foundation of sand.
Exactly. One of your sources put it this way. Imagine trying to build a house on a foundation full of cracks and holes. That's what it's like trying to do data science with bad data.
So bad data equals bad outcomes. It's not just a technical issue.
It impacts the bottom line for sure. Your research shows how much time and money is wasted just trying to clean up data.
Okay, I'm starting to see why this matters. But what does good data actually look like?
Well, that's where those data dimensions come in. It's like a checklist for evaluating how healthy your data is.
So like accuracy meaning the information is actually correct?
Right. Then you've got completeness is all the necessary info there. Consistency, does it all make sense when you compare different sources?
And there's validity too. Like, does the data measure what it's supposed to measure?
Precisely. Don't forget integrity, so is the data secure and protected. And finally, uniqueness, making sure you don't have unnecessary duplicates all over the place.
It sounds like it's not just about having a lot of data, but having the right data and making sure it's in good shape.
That's it. And that brings us to data governance.
Ah, yes, governance. It's kind of like the rules of the road for data.
Exactly. Think of it as the set of rules and procedures to make sure data is handled responsibly throughout its whole life cycle. Data policies, standards, processes, assigned roles, and of course, security measures.
So data governance is the framework that keeps everything running smoothly and makes sure everyone is treating data with, I guess, the respect it deserves.
You've got it. And to actually manage and improve the data quality within that framework, you need a structured approach. That's where data quality frameworks come in. They help you spot potential problems, figure out where your data stands right now, and create a plan for making it better.
So it's not just reacting to problems, but actually being proactive and having a plan in place to keep the data healthy.
You got it. And that leads us to data quality maturity models.
Maturity model.
Yeah, they help organizations understand where they are on their data quality journey and what they need to do to reach the next level, like a roadmap to data quality excellence.
I like that, a roadmap.
Yeah.
Earlier you mentioned the data lifecycle. What does that involve?
Well, the data science lifecycle is a structured approach that data scientists use to, extract knowledge from data. It usually involves stages like defining the problem, collecting and preparing data, building and evaluating models, and then deploying and monitoring those models.
So data quality isn't a one-time thing. It needs to be addressed throughout that entire life cycle.
Exactly. And that's where information architecture comes in. It's like the blueprint for how information is organized and presented.
So like creating clear labels, making sure things are consistent, and thinking about how people will actually use the information.
Exactly. A good information architecture makes it much easier for people to find what they need, understand it, and use it effectively. And then you have data standards, making sure data is consistent and interoperable.
Data standards, what are those exactly?
They're basically agreements on how data should be represented, formatted, and exchanged, like making sure everyone is speaking the same data language. Crucial for data sharing and integration.
I bet that's super important in healthcare, right? Where you have data going back and forth between doctors, hospitals, insurance companies.
Oh, absolutely. In healthcare, data standards help make sure that all the information about patients, medications, everything can be understood and used by everyone involved.
It would be chaos without them.
Exactly.
So we've covered data quality's importance, the dimensions of good data, data governance, the data science lifecycle, information architecture, and data standards. Anything else we're missing?
Well, we still need to talk about the different types of data and, the specific challenges that come with each one.
Right, like numerical data, text data, images. It's not all the same.
Exactly. And each type needs different approaches to managing data quality. Like dealing with missing values in numerical data might need imputation techniques, while cleaning text data might involve natural language processing.
So it's not a one-size-fits-all approach.
Definitely not. And this brings us to those concepts of goodness of measurement and goodness of fit.
Oh yeah, those sounded interesting. Can you explain this?
Goodness of measurement basically refers to how well your variables are capturing the underlying concept. You want to make sure your measurements are accurate, reliable, and valid.
So if you're measuring customer satisfaction, you want to make sure your questions actually capture what satisfaction means.
Exactly. Goodness of fit, on the other hand, looks at how well your chosen model actually fits the data. It's about finding the best model to represent those underlying relationships and make good predictions.
So you could have great data on customer behavior, but if you pick the wrong model to analyze it, your predictions will be off.
Precisely. Both goodness of measurement and goodness of fit are crucial for ensuring data quality and getting meaningful insights.
Okay, I see the difference. Now, what about bias in data? Why is that such a concern?
Bias happens when your data doesn't accurately represent the population you're trying to study. It could be from sampling errors, measurement errors, or even, intentional manipulation.
Like if you do a political poll, but only ask people from one specific area, the results might be skewed.
Exactly. And bias can lead to wrong conclusions and sometimes even harmful decisions.
So it's really important to watch out for bias and try to minimize it. What about sample size? How does that impact data quality?
Sample size is key because it tells you how confident you can be in the findings. Generally, a larger sample size leads to more reliable results.
Makes sense. So in a medical study, you'd want a large enough sample size to make sure your findings are statistically significant.
Precisely. And the right sample size depends on a lot of factors. The level of precision you need, how much the data varies, and the complexity of the analysis.
Okay, so we need to be mindful of both bias and sample size. What about actually tracking and monitoring data quality in a systematic way? Are there any specific tools for that?
There are. You can use data quality scorecards and dashboards.
Okay, tell me more about those. What do they do?
A data quality scorecard is like a report card for your data. It gives you a summary of key metrics like accuracy, completeness, and timeliness. You can see how your data quality changes over time, spot areas for improvement, and even communicate the status to stakeholders.
So a quick snapshot of data health, basically.
Right. A data quality dashboard is even more visual. It uses charts and graphs to make it easier to see trends and potential problems.
Like a control panel for your data. You can see how it's doing and where you might need to step in.
Exactly. You can even set up alerts to let you know if the metrics dip below a certain level.
Very cool. Now, data quality isn't just about the technical stuff, is it?
No, not at all. It's about people, processes, and the whole organizational culture.
Are there any frameworks for addressing those broader aspects of data quality?
There are a couple that are pretty interesting. The data science hierarchy of needs and the machine learning adaptation of Bloom's taxonomy.
Those sound intriguing. Can you break them down for me?
Sure. The data science hierarchy of needs takes inspiration from Maslow's hierarchy of needs, saying that certain basic data needs have to be met before you can move on to more advanced things. So you need to have high-quality data, strong data pipelines, and clean, prepared data before you even start thinking about building models.
So don't get ahead of yourselves, basically. Make sure the foundation is solid first.
Right. And Bloom's taxonomy, which was traditionally used in education, has been adapted for machine learning to help understand different levels of learning models and how they relate to data quality. It emphasizes that it's not just about storing data, but actually using it to generate insights, predictions, and even create new data.
So going beyond just describing the data to actually using it in more sophisticated ways.
Exactly. And as you move up those levels in Bloom's taxonomy, the demands on data quality increase. The more complex your models are, the more important that high-quality data becomes.
Okay, I see how that all ties together. But how do we put all this into practice? What are the actual steps to ensure good data quality in our projects?
Well, the first thing you need is a clear data quality strategy.
So a plan of attack.
Exactly. You need to define what you want to achieve, understand what could cause problems, assess where your data stands now, and then pick the right techniques to address those issues.
A roadmap, just like you mentioned before.
Exactly. And as part of that strategy, you'll need to think about things like data flow, region control, and lineage tracking.
Right. Those came up earlier. Remind me what those are about.
Data flow refers to how data moves through an organization or system. It's important to understand how it's collected, processed, stored, and used so you can spot potential points of failure.
So like mapping the journey of the data.
Exactly. Version control helps you track changes over time. It makes it easier to fix errors, go back to older versions, and ensure your analysis is reproducible.
So like having a history of all the edits to a document.
Exactly. And lineage tracking goes even further, giving you a detailed record of where the data came from, how it was transformed, and how it's being used.
So like a family tree for your data.
That's a great way to put it. And all of these things, data flow mapping, version control, and lineage tracking, are key for building trust in your data.
Okay, that's a good overview. But let's zoom in a bit. What about specific techniques for preparing and cleaning the data itself?
Well, there are the three categories we touched on: data cleaning, data transformation, and data reduction.
Right. Can you give me a quick rundown of each one?
Sure. Data cleaning is about tackling those common data quality problems: missing values, inconsistencies, errors, and outliers. It involves techniques like imputation, outlier detection, and data validation.
So basically getting rid of the bad stuff that could mess up the analysis.
Exactly. Then you have data transformation, which is about making the data more suitable for analysis.
So converting variables, rescaling them, things like that.
You got it. Don't underestimate data transformation. It can make a big difference in the accuracy of the results.
Okay, I see how each step builds on the last one, making the data better and better.
Right. And finally, there's data reduction, which helps you manage the volume of data without losing valuable info.
That's where you use techniques like dimensionality reduction, feature selection, and data aggregation.
Exactly. Dimensionality reduction shrinks the number of variables. Feature selection helps you pick the most relevant ones. And data aggregation combines data points into summaries.
So it's all about simplifying the data without losing the important stuff.
Precisely. These reduction techniques are especially important with huge data sets because they can make processing much faster and more efficient.
Earlier you mentioned missing values. Can you tell me more about the different types and how they're handled?
Sure. Understanding why data is missing is crucial for choosing how to replace those missing values.
So we're not just filling in blanks with random numbers.
Definitely not. There are different types of missingness, each needing a specific approach.
Can you give me some examples?
One common type is missing, completely at random, or MCAR. In this case, the missing data has nothing to do with other variables in the dataset. It's like those data points were randomly deleted.
So like if you had a data set of customer purchases and some purchase dates were missing, it wouldn't necessarily mean anything about those customers or their habits. Maybe it was just a data entry error.
Exactly. In those cases, you can often use simple methods like mean or median imputation to fill in the missing values.
So you'd replace the missing purchase dates with the average or median purchase date for all customers.
Right. But it gets more complicated when the missingness isn't random, like with missing at random, or MAR. Here, the missingness depends on other variables that you do have.
So like if people with higher incomes are less likely to report their income in a survey.
Exactly. You can't just use the average income to fill in the blanks because that would bias your data.
It would make everyone look like they have an average income.
Right. In those cases, you need more sophisticated techniques like regression imputation, which takes into account other variables to estimate those missing values.
So it's like detective work, trying to figure out what the missing value should be.
That's a great way to put it. The more you understand about why data is missing, the better you can handle it and make sure your analysis stays accurate.
Okay, that makes sense. Wow, we've covered a lot of ground in this first part of our deep dive. Data quality, dimensions, governance, the data science lifecycle, information architecture, data standards, types of data, goodness of measurement and goodness of fit, bias, sample size, scorecards, dashboards, hierarchy of needs, Bloom's taxonomy, strategies, data flow, version control, lineage tracking, pre-processing, missing values, imputation.
It's a lot, I know, but we're just getting started.
I'm excited to keep going. Before we move on to the next part, should we do a quick recap just to make sure we're all on the same page?
Sounds like a good idea. Let's take a moment to go over what we've covered so far.
Okay, we started by talking about why data quality is so crucial, especially with all the big data and AI we're dealing with these days. We saw that bad data can lead to bad analysis, bad predictions, and ultimately bad decisions.
And it can cost a lot of time and money with all the cleaning and preparation involved.
Right. And to address this challenge, we talked about the key dimensions of data quality: accuracy, completeness, consistency, validity, integrity, and uniqueness. These are like the building blocks for evaluating how healthy our data is.
We also discussed data governance, which is essentially the set of rules and procedures to ensure that data is handled responsibly throughout its entire life cycle.
And we can't forget about those data quality frameworks and maturity models, which give us a structured approach to managing and improving data quality.
Right. We also touched on the data science lifecycle, information architecture, and data standards, emphasizing how they all play a role in making sure data is accessible, understandable, and easy to work with.
We also talked about how different types of data need specific approaches to quality management, and we explored those concepts of goodness of measurement and goodness of fit.
We also touched on the importance of identifying and minimizing bias in data, as well as choosing the right sample size for your research.
And we introduced some tools like data quality scorecards and dashboards, which help us track data quality metrics and spot potential issues.
Right. And then we talked about the data science hierarchy of needs and the adaptation of Bloom's taxonomy for machine learning, which give us helpful frameworks for understanding the foundations of data science and different levels of learning models.
And finally, we talked about the need for a clear data quality strategy, as well as techniques like data flow mapping, version control, and lineage tracking. These help ensure data quality throughout the entire process.
Whew. That was a pretty comprehensive recap.
I think we're all on the same page now and ready to continue our data journey.
Let's do it. Welcome back, ready to roll up our sleeves and get a little more hands-on with data quality.
Let's do it. We talked about garbage in, garbage out, so let's talk about cleaning up that garbage. Data pre-processing, right?
You got it. This is where we really transform that raw, messy data into something usable.
It sounds like this is where the magic happens. So walk me through it. What are the techniques?
Well, remember we talked about data cleaning, data transformation, and data reduction. Think of them as the core tools in our data science toolkit.
Okay, let's start with data cleaning. What exactly goes into that?
Data cleaning is all about tackling those common data quality gremlins. Missing values, inconsistencies, errors, and outliers.
So like scrubbing the data clean, making sure it's actually accurate.
Right. You might use imputation for those missing values, identify and correct errors, and even remove outliers that could skew the analysis.
Makes sense.
Yeah.
And you'd use data validation to make sure everything meets the standards.
Exactly. It's like having a quality control check for your
I
data.
like that. So once the data is clean, what's next?
Then we move on to data transformation. This is where we reshape and refine the data to make it more suitable for analysis.
So like converting variables, rescaling them, or transforming the data to fit a specific distribution.
You're catching on quickly. These transformations are crucial. They can seriously improve the performance of your models and how accurate your results are.
I'm seeing how each step in this process builds on the last one, making the data more and more refined.
Exactly. And then comes data reduction. That's where we manage the volume of data without losing those important insights.
Right. Techniques like dimensionality reduction, feature selection, and data aggregation. They all come in here, right?
You got it. Dimensionality reduction helps you reduce the number of variables. Feature selection helps you choose the most important ones. And data aggregation lets you combine data points into summaries, making the data set smaller overall.
So it's about finding the signal in the noise, basically. Getting to the essence of the data.
That's a great way to put it. These data reduction techniques are super important when you're dealing with massive data sets. They can really speed up processing and make your analysis more efficient.
We talked about missing values earlier and how it's important to understand why they're missing. Can we dig a little deeper into that? What are some of the different types?
Of course. Remember, understanding those reasons is key for picking the right way to replace those missing values, what we call imputation. Different types of missingness need different approaches.
So it's not as simple as just filling in the blanks with random numbers.
Definitely not. One type we see a lot is missing completely at random, or MCAR. Here, the missing data is totally unrelated to any other variables in the dataset. It's like those data points vanished randomly.
So if we're looking at customer purchase history and some of the purchase dates are missing, it might just be a random error, not something about those specific customers.
Exactly. In those cases, you can usually use simple techniques like mean or median imputation.
You just replace the missing purchase dates with the average or the median date for all customers.
Precisely. But things get a little trickier when the missingness is not random, like with missing at random or MAR. This is when the missingness is linked to other variables in the dataset.
So going back to that survey example, if people with higher incomes are less likely to report their income.
You got it. In those situations, you need more sophisticated techniques, like regression imputation, which uses other variables to estimate those missing values.
It's like you're using clues to solve a mystery, right?
Yeah.
Figuring out what those missing values should be based on the information you do have.
I like that analogy. The more you understand why data is missing, the better you can handle it and make sure your analysis is on point.
Okay, I'm getting a much clearer picture now. We've talked about all these different techniques for cleaning, transforming, and reducing data. But how do we actually know if our data meets those quality standards we talked about? What kind of tests can we run?
There are a ton of data quality tests you can use, each focusing on a different aspect of data quality. For example, null value tests check for missing data, range checks make sure your numbers fall within expected limits, and pattern checks validate things like email addresses or phone numbers.
So it's like having a whole toolkit for measuring different aspects of your data.
Exactly. There are also tests for referential integrity, making sure relationships between different tables in a database make sense, and tests to confirm your data types are correct.
And for text data, you'd probably use things like natural language processing to catch spelling errors and grammar mistakes.
Right again. And the best part is, many of these tests can be automated and built right into your data pipeline, so you're continuously monitoring for problems.
That's super helpful. Now, I'm a very visual person.
Hmm.
What about those interactive visualization tools? How do they fit in?
Oh, interactive visualization tools are amazing for exploring, understanding, and even cleaning your data. They let you see patterns and trends that might be hidden if you're just looking at rows and columns of numbers.
It's like bringing the data to life.
Exactly. You can create histograms to see how the data is distributed, scatter plots to explore relationships between variables, and box plots to spot those pesky outliers. And you can use dashboards to track data quality metrics over time and see where you need to make improvements.
So it's like having a visual control panel for your data. Can you give me some examples of specific tools that people use?
Sure. There are plenty out there. Tableau, PowerBI, and ClickSense are popular for building interactive dashboards. And then you have Python libraries like Matplotlib and Seaborn for creating visualizations, both static and interactive.
Lots of options then.
Exactly. You can choose what works best for your specific needs and the type of data you're working with. The great thing about interactive visualization is that it lets you engage with the data in a more intuitive way. You often uncover insights you wouldn't have seen otherwise.
This has been super helpful. We've gone over all sorts of techniques for cleaning, transforming, and reducing data, how to deal with those missing values, how to test for data quality, and all about those cool interactive visualization tools.
It's a lot to cover, but it's all essential for ensuring you're working with the best possible data.
It's been fascinating, but I feel like we've only scratched the surface. I'm ready to see how these techniques are actually used in the real world.
Me too. Let's move on to the last part of our deep dive, where we'll explore some real-world applications and see how all of this comes together.
Welcome back. We've covered a lot of ground, exploring all the key concepts of data quality. Now, let's see how it all comes together in a real-world setting. Healthcare.
Healthcare is a great example because it's overflowing with data from everywhere. You've got electronic health records, medical imaging, insurance claims, clinical trials. The list goes on. The challenge is harmonizing all of that data, bringing it together in a consistent format.
That sounds incredibly complex, like piecing together a giant puzzle, but all the pieces are from different puzzles.
That's a great analogy. It's definitely not easy, and it requires meticulous attention to detail. The first step is establishing clear data standards. We need to make sure everyone's speaking the same language when it comes to things like patient demographics, diagnoses, medications, all of that.
So if one hospital uses one code for heart attack, and another uses a different code, you need a way to translate those codes so the data can be combined accurately.
Exactly. Then comes the data cleaning and transformation. We need to catch those inconsistencies, fix missing values, and make sure all the formats are standardized.
It sounds like this requires a deep understanding of medical terminology and coding. It's not just about fixing typos, it's about making sure the data is accurate from a medical perspective.
Absolutely. And throughout all of this, we have to be incredibly careful about patient privacy. You can't just throw all of the sensitive data together without taking precautions. We need to de-identify the data, removing all personally identifiable information before we can use it for research or analysis.
So it's about finding that balance between using this valuable data and making sure patient privacy is protected.
Exactly. This is where data governance is crucial, making sure that everything's handled responsibly and ethically at every stage. But even with all the challenges, the potential benefits of harmonizing healthcare data are huge.
I can imagine. What kind of possibilities does it open up?
Well, think about it. By combining data from all these different sources, we can get a much more complete picture of individual patients, entire populations, and even specific diseases. This can lead to more personalized medicine, better ways to prevent diseases, and even new cures.
It sounds like data is playing a bigger and bigger role in improving healthcare.
It definitely is. We're moving towards a future where data can empower healthcare professionals and make a real difference in patient outcomes.
Now let's go back to a concept we touched on earlier, Gold labels and silver labels. Can you refresh my memory on those?
Sure. Gold labels refer to data that's been labeled manually by human experts. This is often seen as the gold standard in healthcare because it involves clinicians carefully reviewing and annotating data like medical images or pathology reports.
So if you're training a model to detect cancer cells in a biopsy image, you need a data set where each image has been labeled by a pathologist to say whether or not cancer is present.
Exactly, those expert-labeled images would be your gold standard. But getting those gold labels can be really time-consuming and expensive, especially when you're dealing with a lot of data.
And that's where the silver labels come in.
Right, silver labels are generated by algorithms. Machines can process tons of data much faster than humans.
So you could use a pre-trained model to create initial labels for those biopsy images, and then have pathologists review and refine them, essentially turning the silver into gold.
Exactly. It's a way to combine the speed of machines with the accuracy of human expertise. And this leads us to a really interesting frontier in data science: synthetic data.
Synthetic data. I'm not familiar with that.
Imagine creating a digital twin of a real data set, but without any of the actual personal information. That's what synthetic data is. It's artificially generated data that imitates the statistical properties of real data.
So you could have a synthetic data set of patient records that has all the same patterns and relationships as a real data set, but without any real names or identifying information.
Exactly. This opens up so many possibilities for research. You can explore different scenarios, test treatments, even create personalized plans, all without risking anyone's privacy.
Wow, that sounds incredibly valuable.
It has a lot of potential to transform healthcare research, and as the technology keeps getting better, we'll see even more uses for it.
Well, this has been a fantastic deep dive into the world of data quality. We started with the basics, then dove into all the techniques, and now we've seen how it all applies in the real world.
You said it. And I think the key takeaway here is that data quality is a continuous journey. It's not a one-time fix. As we get more and more data, we have to stay on top of it, using the right tools and techniques to ensure our data is reliable and ready to be used.
Couldn't have said it better myself. And to everyone listening, we encourage you to keep learning and exploring this fascinating world of data. Happy data diving.